Okay, guys, I guess this is what we got, and I hope you guys are all doing well. I apologize there for the 1 hour delay there today. We had I had a meeting there, and with kids and all this kind of stuff there, just had to push this back. So hopefully I didn't inconvenience anyone there too badly. We're looking at probably, I'm hoping, about an hour and 15 minutes, hour 20 minutes. We'll see how it all goes. What we're going to be doing there starting off is I'm going to look at the lab that I put out there yesterday. It's not too bad. And then I'll talk about the quiz there that's coming out after class there today. If anyone's here in my chemistry, I used... for my chemistry quiz there last week, I used a new program called a Kindy, where it emails you the test and you fill in the bubbles and it does all the rest. I don't know, it just seemed like a little bit more work. So what I did was I put the quiz right on Blackboard, which I think you guys are pretty familiar with. So that'll open up there this afternoon after class. But I hope you guys are all doing well. Boy, we only have 2, 4, 6, 7. Well, that's all right. We're recording it anyway, so this will be posted there to YouTube afterwards. But how are you guys doing? You guys okay? Are you guys coping? Silence will be deemed as coping and double thumbs up. Hi, Mallory. All right, Joanna, I like it. Because things are going to start to get busy. And I don't know if you guys have... I know there for the first semester of pre-health, you guys... here, I'll start my video here. There we go. I know for the first semester there of pre-health, you guys had, 5 classes? And I think now you guys might have 6. It does get hectic. But do not lose sight of what's going on. Things are going to get quite busy. In fact, that you guys probably won't even wake up until week 7. The chemistry there, we've got, no quiz there this week, I think, but the assignment goes out. There's another quiz next week, another lab next week. For physics there, you guys have got your lab there this week. That's due in a week. You've got a quiz to do. Next week, in physics there, we have our first big exam. Bang, it's here. So if you're having any issues now, please let me know, okay? Because we can fix these kinds of things, all right? If you're starting to feel stress, that's good. Acute stress, short-term stress is great. It actually makes you stronger, all right? Just like the song says, all right? But long-term stress is not good. So manage your time well. And if you're having any issues, please let any of us know, okay? Let's share a screen, shall we? All right, now, what am I doing? Is that it here? Lab 1. Okay, so here is, I didn't want that one. I wanted this one. This is what I want. PR Labs, Lab 1. So this is the lab there that I put out. And it's up on Blackboard. You can have have a lab partner. Why not? You know, but don't miss out on the opportunity. Like, if you have a lab partner, great. Both of you guys do the lab and then meet in the middle somewhere. Or, you know what I mean, do half and do half. But if you're only going to do half, make sure that the other person teaches you how to do the other half. Right? Because the reason I put this out here is because this is exam stuff. You have your first exam next week. All right? What are these guys worth? 12% each? So it's a good chunk. All right? And hit it hard. Because I tell you, this course is not going to get any easier than these first 3 weeks. All right. So if you're going to bang out an exam and get your 98%, this is the one. Okay. So here's your lab here. It's broken up into the 4 sections, section A, B, C, and D. I hope my math is correct. If it's not, I'm sure somebody will tell me. And basically this lab is self-contained. You know, all of these formulas, even though they're kind of written wonky, they're the same formulas there that are on your sheet. And it gives you a question there, an example, how to do something, and then 3 questions. And I've highlighted the questions there in yellow because this lab is, I wouldn't say it's long. Okay, maybe it's long. But it looks long. It's not long. All right? It'll take you at least an hour or so to do it. And so here are some questions there. Write your answers right in here. Whoopie-doo. Okay? Section A there is average speed. All right? And you guys know the difference between speed and velocity. If you don't, have a look. Okay? Tells you all these different things here. There's your formulas. And even gets into how to do one of these graphs. Like this is a distance versus time graph. Write that one down. Distance versus time graph. Okay? That measures the amount of distance you travel over a certain amount of time. Speed. So from here you can calculate, you see, you take, like if the question was, what's your, like you have a look here between 0.1 seconds. Why is that not letting me see? In 0.2 seconds, you could just calculate, okay, the car was at 20 centimeters here at 0.1 seconds. The car was at 40 centimeters at 0.2 seconds. And look at the information that we can get. So have a look at this. I didn't really go too much into these time graphs. And that's why I kind of left it here for the lab, for you guys to do a little bit of investigation. And by the end of it all, you guys are all talk and communicate, which I hope you guys do on the outside. All right? And teach each other. Because that's how this is going to work. Okay? Here we've got, this section here. And these are all position versus time. So it's exactly the same as this one here. Okay, position versus time. Okay. And we can calculate velocity. And if you have a look at these right here, these are the things that I'm looking for. Is do you understand what's happening here? And like you look at this one right here, position. Is that in meters, right? So at 1 second, it was at 0. At 2 seconds, it was at what? I don't know, what is that? 2.5 meters. And you see what's going on here. So it's moving. Like, what does that seem to you? Like, it's moving the same amount of distance, basically, every interval of time, right? So, what do you think is going on here? Constant speed, maybe?
So, it's not... Sorry to just jump in.
No, it's all good.
So, this is because the position is changing, but the speed's not necessarily changing, so it's just going further, but it's going at the same speed.
Yes, and don't think, don't think that this car is moving to the right at all. This is just demonstrating you that the car is going forward at a constant speed.
Okay.
You know what I mean? Like, so it's like a sprinter, and he's going directly forward at a constant speed. Yeah. Question, talk to me.
I just misinterpreted it because I just read the graph wrong. I flipped to the axes. So to me it looked like it was speeding up, but now that I look at it again. It's the other way around. So
Good.
it's going at a constant speed.
Exactly. Like that's what these ones are. And all I'm looking for is like if you write 6 words in this space, you know what I mean? I kept it short for a reason. Just tell me in 3 or 4 words what's happening here. And I'm going to be totally forgiving, you know what I mean? But I like these. They're quick, they're easy. Tell me what's happening to this object. Like you look at this one, these are all the same, position versus time, so distance versus time. So you're reading the graph is going to be the same for all of these guys, whether it's speeding up, slowing down, constant speed, these kinds of things. Question?
Yeah, so the one beside it, where it's kind of going up in a goo and like a little thing, with that there's this change in speed there.
Well, have a look. No. Again, this is a distance versus time. So at 1 second, it's at what? 1 meter? Is that what that says? My eyes are crap. And then at 2 seconds, it traveled another meter. And then at 3 seconds, it traveled 2 meters. And then after another second, it traveled 4 meters. And after another second, it traveled, I don't know, what is that? Up to 16. So your time interval, 1 second, 1 second, 1 second, 1 second. But what's going on with my distance traveled within that second? Well, it's 1, 1. Go ahead. Yes, okay. So if your distance is traveling as compared to another second of time, and it looks like it just might be going faster.
Okay, so it's speeding up over time.
That would be a good assumption. Good. Okay. I am happy. I'm happy. And these guys here are all distance versus time. All right, just to be clear. And I'm just looking for a couple of words in here. Just tell me what's going down. The next section here, okay, again, nothing you haven't seen before if you've done the questions at the end of every chapter. And kick out some numbers for me. That's all we're looking for. Okay, now we're moving into velocity. Section B. Now we're into acceleration. Now, we're going to go back and deal with acceleration again there today. And you remember the Newton's, we're going to get into Newton's first law of inertia and these kinds of things there today. But acceleration doesn't necessarily mean speeding up. Yes, it does mean speeding up, but it can also mean slowing down. And we use a word deacceleration, but actually isn't even a word. But acceleration just means a force applied to an object that makes it change speed. All right. We'll get into all this there more. It'll make a lot more sense after today's lecture. Now, this section here, you'll notice our graphs. They'll be a little different. And you see here, these are not distance versus time graphs. They're velocity versus time. So, what we have a look here now, and if you go back to these ones here from before, it was distance and time. And speed is equal distance over time. Well, here we have velocity, which is, you'll see here, there's 2 units, meters per second. And then we have a third unit here. Velocity is meters divided by seconds. And then we have another seconds over here. Well, if you have a look at acceleration, acceleration is equal to meters per second squared, which is exactly one of these graphs. So, let me be clear. If you see a position over time graph or distance over time graph, okay, you're going to be talking about the speed or the velocity. Okay, the speed, meters per second. If you're looking at one of these acceleration, or sorry, velocity versus time graphs, you're not going to be dealing with, you're not going to be one to tell me about there the velocity. You can, but really what we're looking at therefore is the acceleration, the change in speed. So you have a look here, and Now, at 1 second, I'm traveling at 20 meters per second. At 2 seconds, I'm at what, 17? 3 seconds, I'm at 15 meters per second. At 4 seconds, I'm at 14. And you'll see what's going on here. What's going on with my speed? What's going on with my acceleration? Probably looks like I'm kind of slowing down. How am I slowing down? Am I suddenly slowing down? Probably this is telling you there that I'm gradually slowing down so that by second 10, I'm really only traveling about 2.5 meters per second. And see, same thing here. Look at my speed, 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 speed. What's happening there too? I have a positive acceleration, a negative acceleration. So have a look at these. Once you kind of see them, then they become pretty cake. Like this one here. Don't freak out. It's a velocity versus time graph. No difference than this one. And what's going on here? Have some fun with this. It's kind of a puzzle. Once you get them, then they're all right. And I'm not a tough marker anyway. Give me something and you'll do just fine. This one here is another. Which two graphs represent the same phenomena? So here I have a distance versus time, velocity versus time. Is it this one? This one? Break them down. Understand them. Trying to see what's going on. And one of them represents the same banana. Okay. Here's just some more background information. See, there's your acceleration. 5 meters per second squared. More pre-calculations there, and then you just do these questions right here, and then that's enough for your background questions. All right, and then have a read. This is what the lab there that we do normally, and you take a ramp. Sorry, I don't know what you guys can see. You take a ramp that's like, I don't know, 1.2 meters. I think the one in the lab is actually 1.2 meters. I think I've changed the number though. And you make a mark on the wall at 30 centimeters from the floor, and then make another mark on the wall at 60 centimeters. Okay. And one person holds the ramp, like it's just like a piece of corrugated pipe. That's all it is. And you hold the ramp at the 30 centimeter mark and let it fall down to the floor. So you've got, something like this. And then you put a marble in it. See ya. Time it. These kinds of things. And then you put the ramp at 60 centimeters against the wall and let the ramp go down to the floor, and then throw the marble in and away you go, and you just take your times. This one here is not bad at all. It's just, I'm just ingraining in you guys how to do average speed and velocity. So I've given you guys distance and time here. This is a 30 centimeter chart. Okay, so the pipe is 1.25 meters. The time it took the marble to get down was 4.4 seconds. Calculate your average speed, average velocity. Bang, bang, bang. I think that's 4 marks. Half mark each. Same banana here for 60 centimeters. Info. There you go. Now, here we go from... here we're back at this again, and here I want you guys to start working on your change of velocity and your average acceleration. And where these numbers came from, they came from the first chart right here. Okay, and I just input them into here, and now you guys can figure out your change in velocity based on the previous information. This one here is the same banana, and that's your lab. And please upload it as a PDF. Please have everyone's, your 2 partners, or if it's just you, it's all good in the hood. Have your partner's name, full name, and student number. Okay? So that's your lab in a nutshell. I think you got a week. It's not too bad. And
sorry, I have another question.
No, there's absolutely no sorry. What do you got?
Okay, for the investigation, I just want to make sure that I looked at this correctly. For the investigation, my average velocity and my average speed were going to be the same thing for the first two ones, right? Or am I wrong?
Oh my goodness. That would be interesting. Try it out.
Because you're given the same numbers for the first two. No, sorry, not for this one.
This one.
These two.
Interesting.
Because it's the same number.
Interesting, isn't it?
Because they're starting at 0. So you only have to...
I'll let you guys deal with it. You're on the right track. And so the lab there, if anyone is having any issues with this there, I think people should be able to coordinate if there's no lab part. I don't know if I did or not. But what I'll do is I'll open up a tool box there, I think. Maybe I won't. If you don't have a partner, it's all right. The lab is not bad at all. Honestly, it should take you about an hour. And so have a look at the lab there and let me know how things are going. And other than that, I think all is all right. Are there any more questions about the lab? Great questions, by the way. I love it. Your quiz will come on out there this afternoon. It's not bad. I've just taken questions there. Not the same questions. It's true and false, multiple choice. That's it. And it's on Blackboard. It should open up, I think, 4 o'clock or something like that. There's no time limit. So I think you can stop it and start it. I think you have a week to do it. Other than that, I don't think it's that bad. Everything there, this is week 3 lecture, and your test will be on units 1, 2, 3. So next week there, I'll open up the test, and so basically next week, you'll have a test going on. I'll give you probably a shorter amount of time there to do the test because I probably want to keep it more conglomerated than letting it kind of hang out there for a week like a quiz. So I'll let you guys know there this week. And so next week there you'll have a test. And I will also have a lecture as well. So we'll work it all out there and see how it all goes. But things are starting to heat up. So if you're having any difficulties, just let me know. Did I forget anything? No. Okay, let's go. Welcome to Newtonian physics. All right. Newton. Probably one of the greatest minds of humanity. And it all came from an apple falling on his head. Sorry, just that sun beating down. There we go. Okay. Sir Isaac Newton, the father of modern day physics, and basically changed everything. And this is what he came up with. He basically defined what a force was. And basically a force is a push or a pull. And it causes acceleration in something. So, like, we're going to get into Newton's first law there, which is inertia. And the things like to either be at rest or constantly moving. And what I mean by constantly moving is moving at the same speed in a straight line. But something happens, a force will act upon this object that will disturb its inertia. It becomes unhappy. So objects are happy when they're sitting there doing nothing or moving at the same speed in a straight line. Why? We have no idea. We have no idea. Like if we send a spaceship, you literally only need a minute's worth of fuel if you wanted to travel as fast as we possibly can. currently. You need about a minute's worth of fuel in your rocket ship to get you out of orbit, and then maybe another 10 seconds of flying through space at 30,000 kilometers a second, and then turn the engines off. Because you're going to keep moving at 30,000 kilometers an hour. Because there's no force acting on you. There's no atoms in space. There's nothing in space. There's no friction in space. You will move at that speed for forever without any fuel anymore. That's one of the laws of inertia, which we'll get into there today. This is a really cool, a lot of this stuff there can be applied to biomed and all these kinds of things. So it's good. It's good. Let's have a look. Weight and friction. The most common forces in our life, most common force in our life is weight. Of course, gravity, right? We weigh ourselves. We buy things in weight. Bananas are 49 cents a pound. That's all a weight quantity. Objects are shipped in weight. The force of gravity is acting upon an object. Now, this is one of the huge things that we need to understand there, applied to chemistry as well, is that weight is related to mass, but they're really not the same thing. Mass has a correlation directly to the number of atoms in your body. And you guys know this there, your chemistry, grams is equal to, moles is equal to grams divided by molar mass. There's a relationship there. Mass, number of atoms, okay? But weight has nothing to do with the number of atoms. It's just a measurement of the gravitational effect on the number of atoms you have. So if you're 200 pounds here on Earth, you'll be significantly less weight on the moon because the moon has less gravity, less pull on you, these kinds of things. The force of gravity acting on an object, pulling it towards Earth. This is what we've got here. Is dependent upon two things. Gravity is dependent on two things. Mass of the object and location of the object. If you were at the top of Mount Everest, I think we talked about this there before. Anybody know what the boiling point of water is on the top of Mount Everest? I think it's in the high 70s. Water boils at 70 some odd degrees on top of Everest. Why? Interesting. Another common force in our life is friction. Friction is the force of resistance of motion between two objects that are in contact. My hands here, they are smooth and they are just the most soft caressing hands ever. But if I go like this there, now my hands are starting to heat up because microscopically my hands look like the Sahara Desert. And there's little crooks and nags and bumps and all this kind of stuff that are hitting each other and probably pretty gross. You know, there's skin cells all over the place. All right. Friction, the force of resistance of motion between two objects. There are two kinds. There is static friction and there is kinetic friction. Anybody know here? You don't have to answer. You can just answer me telepathically. Kinetic is just another word for motion, movement. Okay, so you can kind of see what a static friction might be and kinetic friction. We'll get there. Static friction. When there is no relative motion between the two objects in contact. If you try to push your fridge across the floor, you must first overcome the force of static friction before it moves. So static friction is what's keeping everything in place. And if you're going to move something, you've got to overcome this static friction. What's going on here? I'm going to send this to the back. There we go. So example, you rely on the force of static friction when you walk. The friction between your shoes and the ground allows you to propel forwardly. When you walk on ice, the force of static friction is greatly reduced, which is why it's so slippery. So, you know, like when you walk, your toes kind of spread out like this, right? And your foot does the same. It's kind of grabbing on to the sidewalk, all right? But on ice, we walk very differently. We don't walk like this on ice. We kind of, because we don't have that grip anymore. We don't have that static friction. So you have a look here. A couple of examples. In this example here, there's no frictional forces at play. Okay. You have a look here. If we tilt the plane, okay, have a look at the forces that are now acting on this block. The force of gravity now is able to, it's pushing down on this block. Now, if this was a block of ice, it'd be gone. But it's not. Let's say it's a board or, I don't know, just normal flooring. That is also causing friction right here. So the gravity is pushing it down, but what's keeping it up? Okay, there's your static friction. This one right here, if we continue tilting the plane, if the force of gravity is able to overcome the force of the static friction, then this guy will start to move, accelerate. Okay, have a look at those. So we just talked about static friction. Kinetic, which means movement. When there is a relative motion between the two objects, the effects of kinetic friction are often undesirable. You actually, when it comes to comets, meteors, meteorites, I think meteorites are meteors that enter the atmosphere, but I think 99.999% of them never make it because of kinetic friction. These things are coming in at like 10,000 kilometers an hour, and then wham! For 100 million years, they've been traveling through outer space and not hitting an atom, and all of a sudden they fly right into our atmosphere, and they hit the air like a wall. And it pushes the air because these meteors are traveling so fast, same as the space shuttle. And what happens is the molecules of the air start rubbing against the meteor or the space shuttle, and they start creating heat. Okay? And heat enough there that 99% of all meteorites never even make it to the Earth. They all burn up. Galileo, Aristotle, and Newton. Galileo had described an idealized situation with no air resistance, no friction. Aristotle attempted to describe a situation he physically saw. He saw air resistance and friction did exist as well. Newton combined both of their theories in order to come up with the first two of three laws of motion. These are the big bananas right here. Newton's first law deals with, we introduced this there last week, inertia. I think so. Maybe we didn't. An object at rest will remain at rest until acted upon by an outside force. So, if your shoes that you took off at the front of the house, they're still sitting there, right? They're happy. If an object is exhibiting inertia, let's call it happy. I don't know if it's happy, but let's call it happy because it doesn't like to be moved. So if your shoes are at the front door, they're still sitting there. Okay? If you roll a bowling ball down a bowling lane. Now, I don't know, I'm not a very good bowler. I don't know, how long are those bowling lanes? 50 feet? I don't know, 20 meters, 30 meters? I don't know. Let's say we had a bowling lane that was 100 million kilometers long. It just went on until wherever. You know, there's really little friction going on between the bowling ball and the bowling lane. So if we could somehow just roll this thing, it would roll literally forever and at the same speed. Okay, so have a look at number 2 here. An object in motion will remain in motion. That's where it likes to be. So an object at rest will remain at rest And an object in motion at a constant speed will remain in motion until acted upon by an outside force. So those shoes will not move until somebody moves them. Boy, it took the third week of physics for me to actually say that, eh? You guys would have never have thought. An object will stay in motion at a constant speed until a force acts on it. So this is this whole idea of inertia. Inertia, an object likes to be doing the same thing. Doesn't like to be bebopping, scatting all around and changing acceleration and going around a curve and then jumps up on a tree, takes a break, and then goes all... No, an object likes to be not moving or moving at a constant speed in a constant direction. Don't bother me. That's inertia. What happens, though, is we get into the second law, where we get into force, which I've already introduced the formula there to it. And when we get into, remember the property of an object to resist change to their motion, this is inertia. And an external force is one that is caused by some outside thing. Your mom grabbing the shoes, there's the outside force, okay, which disturbs the shoes' inertia. The shoes are not happy that your mom moved them to a different place inside the closet, all right? But still, the point is, the shoes were exhibiting their inertia. They were happy. They were sitting there in the hallway, and then they could only be moved until an outside force moved them. This is a really, really good movie. Can't play it. And I had big trouble there last week there when I tried to click on something there in my chemistry class. So I'm not clicking it. You guys can. Please have a look at it. All these movies are great. So you guys can go back once the movie or watch it now or whatever. But I'm going to keep moving on. Just more about inertia here. One of the simplest examples of Newton's first law occurs when you're driving and suddenly slam on the brakes. Like, I think, I don't know, was it my mom or my dad or someone telling me there that it took the U.S. government, and I think it was 30 years to mandate seatbelts into cars because people just didn't believe that there was that much of an issue. And like, you're sitting in your car and the car is traveling 70 kilometers an hour. We have a seatbelt in there because if you didn't have a seatbelt and you slammed on the brakes, at that particular second, you are still traveling 70 kilometers an hour. And that's your inertia. You've been traveling this whole time at that, and you like to be traveling that. Even when you slam on the brakes, your body's inertia goes, oh man, I want to keep going 70 kilometers an hour. Well, thank goodness you have your seatbelt on. So there's a classic case of inertia. And why it happens, we don't know. The things just like to be moving how they're moving. Or not moving at all. You and your car become one system. And it's not even just you and your car. Like, you ever tried to flip a coin in the car? Like, you think about this. At, I don't know, 57 seconds, you're 50 meters. And then 58 seconds, I don't know, you're 75 meters. So within 1 second, I don't know, what did you travel, 20 meters? Within 1 second, you travel 20 meters. Well, then how can you flip a coin in the car? Because you're sitting in the car, you have your own inertia. And you've got your 25 cents, it has its own inertia. And you guys are both traveling at 70 kilometers an hour. You flip the coin, and if you flip it, you're moving forward. It's almost like, is the coin going to fall into the back seat? But it doesn't, because the coin is also traveling at 70 kilometers an hour. So the coin's got its own inertia. All right. More on inertia. This kind of comes to the same thing here. An example of an argument against a moving Earth in Copernicus's time. A bird is sitting on a branch directly over a worm. The bird dives straight down to get the worm, but the world is moving, right? It was argued that this would be impossible if the Earth was in motion. The split second it would take the bird to drop to Earth, the Earth and the worm would have moved. So the bird would have missed it. Kind of like me just talking about the coin going in the back seat. Therefore, since birds do catch worms from the trees, the Earth had to be at rest. So, what is wrong with this argument? Think about reaching for your coffee in the car while sitting in your car. Well, if you go and grab your coffee, well, your coffee hasn't moved. Everything is kind of moving with the same kind of inertia. And that's really bad to say because everything has its own inertia. But since the coffee, the quarter, me, we're all in the car, we're all traveling at 70 kilometers per hour. So therefore we basically created our own little universe. Okay? Yeah. Here we go. This is this flipping a coin in the car. The coin, even though it's in your hand, you flip it. Sorry, I'm just trying to find the camera. The coin is independent of you, but you flip it, and now it's on its own. It's still moving forward because it still has that inertia. It's still traveling at 70 kilometers an hour. Okay, so that's inertia. All right. Second law. What happens when something's traveling at 70 kilometers an hour and I knock it off? There's this outside force, okay? A force is the only thing that can disturb an object's inertia. And you look here, the greater the mass of an object, the greater the force required to accelerate it, knock it off its path. So if something's smaller, you're not going to need a greater force to interrupt its inertia. But something that has a big mass, like an elephant, you're going to need a huge force in order to move that elephant. Therefore, force. And you have a look here. I break this down with a couple of questions here. There are lots of questions there that we're going to do as well. There's questions there with answers that I've included there in the weekly. But you have a look here. This is really, really interesting to note. If you look at these, look at this formula. Force is equal to mass times acceleration. Force is directly proportional to mass and acceleration. Mass is inversely proportional to acceleration. So, the bigger the mass, the bigger the force. The bigger the mass, the smaller the acceleration. So an elephant, you're going to need a big force to move it a little ways. I got more stuff that I'll move into there with these guys here. Defining terms, this one here, I put this one, I think all the formulas are on the, I updated the formula sheet. So thirsty, it's water. Yeah. But the sun just right in my eyes. This one here, I will expect you to know, I think it's on the quiz. Force, like with distance there, we use meters. For mass, we use grams, kilograms, these kind of things. For force, we measure them in newtons after Sir Isaac Newton. All right. So therefore, 1 Newton is equal to 1 kilogram times, the 1 kilogram meter second squared. Okay, so basically it's the amount of energy needed to move something 1 kilogram, 1 meter over second squared. And you'll see, you've seen this there before from your acceleration. Meters per second squared. is your acceleration formula, if you will remember. Acceleration there, a change in velocity over time. Let's keep going. Example 1 problem. What is the force applied to an object with a mass of 30 kg accelerating at 8 meters per second squared north? So, you guys are all gonna see, do I have my, where's my, just looking for, it would be, sorry guys, I am just gonna go back and get my formula sheet. Nope, right here. And weekly, week 3, and formula. So you'll see here that these are the formulas. I might update it. I put in what a Newton is and these kinds of things. This one here you'll need there for the quiz. Oh, did I just say that? All right, darn it. And have a look at these. These are what you'll need. And I might update. I don't think so. I'm going to go through it again. But this is what you'll need there for your test next week. That's it. I may update it. We'll see. I don't think so. So, what is the question asking you? What is the force? Well, you go to your formula page. What formulas do I have for force? Okay, I got this one, this one, this one, this one. Okay, all right. Now, what information did Ian give you? Well, he gave me kg, and he gave me this, meters per second squared. Oh, yeah, it's acceleration. So he gave me acceleration and mass. Well, there's only one formula that has mass and acceleration. There you go, 30 kg times your acceleration here, and 240 newtons north. Plug, play, next question. That's how these go. You guys will remember these there from a couple weeks ago. You remember, what was it, Sam and an egg and that question, eh? Yes, there is a question like that on the quiz. Have a look here, what's all going down. Several forces are acting on this object at the same time. Find the net force. Remember, force is a vector, so it must have direction. So, even if you kind of take this as a graph, opposites will cancel out. So let's just take east and west. We're just going to try and cancel. Don't look at the top and don't look at the 30 north on the bottom there. We're only looking at 40 and 20. So you see how maybe things can cancel out. I got 40 going east and 20 going west. What do you think is going to happen there? What's going to be the resultant of those two? Well, we're probably going to be going 20 in this direction. 20 east, right? Because 20 west, 40 east, 20 will cancel here. And then you look here. Here we have a total of 30 newtons pushing down. And we got 30 newtons pushing up. So what's happening here? Break it down into two sections and you'll see here that they did up and down first. Okay, 30 newtons minus 30 newtons. So as far as the up and down goes, nothing. Nada. East and west, you'll see there, we've got 20 newtons east, which is what we predicted. So you have a look here, add them all up. So the force, 0 newtons up, 20 newtons east. That's all that is. Okay? And so the end of the question here, the resultant force, 20 newtons east. Hopefully there that makes sense. That's the only force that is prevailing through and not getting canceled out. By the way, wouldn't 20 newtons east be equal to negative 20 newtons west? Yes. You may need that information. They're just opposite and negative, right? So, problem 2. Now, what is the object's mass if it's accelerating at 100 meters per second? So we're continuing on, okay? So what is the mass? We're looking for the mass. What information did I give you? Well, it's continued on, so it's 20 newtons. Okay? 20 newtons east, and it's accelerating at 100 meters per second squared. What's my mass? Well, what formulas do I have with mass? Force and newtons, force and acceleration, same formula here. And here you're looking for mass. So you've got to be able to isolate for, if you guys are having trouble with manipulating algebraic expressions like this, force is equal to mass times acceleration. I'm looking for mass. I got to get rid of acceleration. So it's force is equal to mass times acceleration. What's opposite of times? Divide. So you divide this side by A. You divide this side by A. A's will cancel on this side, leaving you mass is equal to force divided by acceleration, which is what we have here. Plug in your numbers, away you go. Let me know if that is giving you trouble. Do these once or twice, and again, it's kind of like chemistry. Just plug in the numbers and away you go, if I didn't give you a whole bunch of steps to do beforehand. But as I said, this physics program is not designed to hurt you. Okay? We provide everything there. You just got to walk the path. All right? So these aren't too bad. Example number 3. Several forces are acting on an object at the same time. Find the net force. Okay, so what do we got going on here? Have a look at it. Analyze it. Plan it. Oh, that water tastes horrible. Maybe it's the plastic bottle I'm drinking it out of. All right, so you have a look here. I got 10 down, 30 up, 40 east, 20 west. What's happening? So what they've done here is they're going up, down. So what is happening here? I'm going to have a force of 20 newtons pushing up because I got 30 and 10. If anyone's not getting this, just shout and we can go over it. We got time. Solution 2 here. Now we're dealing with east-west. I got 40 east, 20 west. So it looks like... oh, sorry, they went up and down. Okay, that's fine. And what we've got here now... What's going on here? Several forces. Solution 1. So here... Sorry, I'm losing my that water. Oh, putting that water away, man. And so what we've got here, 30 newtons and 10 newtons coming down. So we'll have a force of 20 newtons going up. So now we've got 40 and 20. What's happening on here? All right, we got 40. And this is 40 going east and 20 going west. But we could also call this negative 20 going east. If you, so just to recap, this number here, 20 newtons going west, can also be called negative 20 newtons going east. So the opposite direction, negative number. Okay? And so they've got 20 newtons. Those two cancel there. So now, this is what's happening here. I got 20 newtons pushing this way, 20 newtons pushing this way. What's going to happen? Therefore, the force will be up and to the east. So we've got 20 pushing this way, 20 pushing this way. It should be going up here somewhere, correct? Aha, there we go. And you see here, because we had the same force pushing up, pushing east, okay? You'll see there that what I've done is this guy here, I brought that line up here from the center. And this line here, I brought it up over here. Doesn't matter if you brought that one here and this guy up here, you're going to get to the same spot. All right, so that's what we want. And we know that this is a right angle triangle. A, B, C is your hypotenuse, and you can figure out, and we get an answer of 28.3. So now your force is 28.3 newtons going this direction. And now we need to find this direction. Okay, you guys have, well, now that you have opposite, adjacent, and you even have your hypotenuse now, you can use sine, cosine, tan. I know, you thought that I'd forgotten about those, but those are going to be there too. So you look at this one right here, and using, here we use tan, you could use sine, you could use cosine, and you'll find there the angle. So this, because this was 20, this was 20, it's going to go up at a perfect 45-degree angle, and there is your Newton force. So therefore the net force is 28.3 newtons in the direction east of north, or north. I would take northeast. Now this was like a 6-slide, I'm just looking at it now. Ugh. Okay, one, you don't have to take it 6 slides. This can be done very easily. I drawn it out to, A, to be kind of painful, B, to help make sure everybody understands. But don't make this question difficult. It's not bad. All right? Once you see it and you start to recognize what's going on, you have your formula sheet right there all the time. You have your lectures right there all the time. You have everything there. You guys should be good to go. Newton's second law of motion. I was looking at this. I'm going to try and find this again. And this was really good. But what I really wanted to show you here is there's this one and there's one more as well. See if this will...
Weight and mass are different things. Whereas mass is a measure of the quantity of matter in an object, weight has meaning only in the context of gravity. Although both the astronaut and the satellite are effectively weightless in this environment, the astronaut has great difficulty imparting a spin to the satellite because it is so massive. It requires less effort to spin an object with less mass.
Perfect. We're getting there for a reason. Mass versus weight. Newton's second law is this one right here. Okay? His second law is force is equal to mass times acceleration. First law is inertia. The rock likes to be sitting on the ground, not moving, or the rock likes to be in a steady, straight line motion at a constant speed. The only thing that will take that rock out of its two situations of inertia is some force. And this is such an important idea that it was given its own law. And that's number 2 here, where force is equal to mass times acceleration. And we can augment this formula to make this guy right here. Force is equal to mass times gravity. Same, because gravity is acceleration. You're increasing your speed as you fall down, and it's at 9.8 meters per second. Same formula. Force is equal to mass times acceleration. Force is equal to mass times gravity. So, example. What is the weight of a 2 kilogram brick on the Earth's surface and the surface of the moon if the force due to gravity in the moon is 1.6 meters per second squared? Well, you look at this number here. What's the force of gravity on Earth? 9.8 meters per second squared. The force of gravity on the moon is only 1.6. So, a 2 kilogram brick is getting a force of 19.6 newtons. On the on the moon, that same brick is only getting 3.2 newtons of force exerted on it. So that's why if you were on the moon and you had that 2 kilogram brick, you could probably throw it 10 football fields because it's just moving. Okay? It's not that light at all, or sorry, not that heavy. Moving on to the second law, keeping with the second law, but moving on to something a little different. We covered it there last week there, centripetal force. And it's just the whole idea of something going around in a circle. And if you think about it, if something's going around in a circle, things really only move in a straight line. Because as soon as you turn, okay, you've turned now, you're still moving in a straight line, but straight line, 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 all the way around the circle. Okay? So when you are going around a circle, like an on-ramp or an off-ramp there from the highway, or on a carousel at the carnival or something like this, you're constantly changing speeds. You're constantly accelerating. And it always works opposite. And you remember last week there we used the analogy there, a book on the bus. If you left your textbook on the seat of the bus, it travels in the opposite direction of the bus as it turns. Well, moving on from this right here, a force acting sideways on a moving object causes centripetal acceleration. The object moves in a circular path as long as the net force remains perpendicular to the velocity. Okay, opposite, right? So here we've got our formula there from the second law. Force is equal to mass times acceleration. But you will remember this formula there from week 2. I have it here. There, and I apologize. I tried to make that C subscript, but it wouldn't go. So that is the acceleration there for centripetal force. Okay, so this formula right here is the one there that we've got right here. So if this is your acceleration there for centripetal force, substitute it in here. We get force is equal to mass times velocity squared divided by the radius. And again, you don't have to memorize it. It's right here. Okay? And I've even broken it up into weeks. Let's have a look here. Now, the way I want you guys to look at this question is, what is going to happen? How do you know what formula you're going to use? Are you traveling in a straight line? You know what I mean? Honestly, that's the hardest part about this course. What formula am I going to use? So you hear, an airplane with a mass of 2,000 kg is observed to be accelerating at a rate of 4 meters per second squared. What is the net force acting on it? Well, you're looking at that. Okay, asking for force, so whatever formulas I have out there for force. Giving me kg, giving me meters per second squared. Meters per second squared, ding, 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 ding. Acceleration. So here I've got mass, I've got acceleration. Throw in your numbers, away you go. Okay. We're going to get into some there that maybe you won't know what formula to use. So you may have to play, but we'll get there. These ones here are more comprehension. I really like them. Considering the current climate, my ability to provide these in a testing situation is limited. I will try, but a jet is cruising at a constant speed of 1,000 kilometers per hour when the thrusting force of the engines is a constant 100,000 newtons. What is the acceleration of the jet? what is the force of air resistance on the jet? So let's have a look here. Since the jet is moving at a constant speed, remember what did we say about something moving at a constant speed? It does not have any acceleration, right? Things like to be moving at a constant, all right? And if they're not changing speed, if they're not accelerating, they don't have any acceleration, right? So thus, since the acceleration is 0, by Newton's second law, the jet has a net force of 0. So going back into the first law, inertia, you know about your two different situations, right? The rock is staying put, the rock is moving straight, and in a straight line at a constant speed. The only way to take that rock out of its inertia is to impact a force on it. But if the rock is just sitting there, or if the rock is moving in a constant speed in a straight line, it has no force on it. All right? So it has no net force. It's happy. So thus the force of the air resistance must also be 100,000. We're going to get more into what air resistance is when we start getting into hypothetical free falls from an airplane. You apply the same amount of force to two separate carts. One cart with a mass of 1 kg and a second cart with a mass of 2 kg. So 2 carts, 1 kilogram, 2 kilograms, and I apply the same force to both. Which of the 2 carts will have the greatest acceleration? And what will that acceleration be? Well, here we go. Flip the formula around. Acceleration is equal to force divided by mass. Since acceleration is inversely proportional to the mass, the cart with a mass of 1 kg will have an acceleration that is twice as fast as the cart with a mass of 2 kg. And I wouldn't ask you something like this because I could totally see how it'll just confuse the bugs right out of your ears. All right? But I just want you to understand, I wasn't looking for a number there. I just wanted to know which one, okay, what's going on with its acceleration. If you have 1 kilogram and 2 kilograms, and if I apply the same force to both, which one is going to have a faster acceleration? Well, the 1 kg. Okay? Which one's going to have a slower acceleration? The 2 kg. So a bigger acceleration, smaller mass. Okay? A smaller mass, you're going to have a faster acceleration. The mass and the acceleration work opposite. What do we got here? An automobile increases its velocity uniformly. I like that word. From standing 0 to 27 meters per second in 10 seconds. The car's mass is 1,000 kilograms. What is the force required to move it forward? Well, here we go. We're looking for force, right? That's what the question says. And this is how I want you to break these down. The only thing the question is asking you is what is the force required to move it forward? Okay, so you find out force is equal to mass times acceleration because it says it on my formula sheet. Force is equal to mass. Okay, I got mass, 1,000 kg, but where's my acceleration? Oh, curses, that Ian, he didn't give me acceleration. Well, I did. You just got to use another formula. Now I gave you time, and I gave you 2 bits of information here. From standing to 27 meters per second. So I have an initial and an end. I have a V2 and a V1 velocity, right? And so you go back into your formula sheet, Acceleration is equal to v2 minus v1 divided by t. 27 meters per second minus 0 meters per second divided by 10 seconds. My acceleration is 2.7 meters per second squared. Well, now there's my formula. Force equal to mass times acceleration. 1,000 kg times 2.7 gives 2,700 newtons. Okay. If you just try some of these questions out, it's all about what the question is asking. That's number one. What is the question asking? And what information did I give you? Same thing there for the chem. I'm going to ask you to find moles, but I'm going to give you molecules. Okay, so you're going to have to flip something before you can actually begin. Welcome to it. Okay, number 5. If an object's mass is 4 kg, so I got mass, and an applied force is acting on it at 12 newtons, and the force of friction is 6 newtons, what is the object's acceleration? Well, here I've got mass, and I got 2 forces. I got 6 newtons for friction and 2 newtons, okay, someone pushing it. Are they going to work in opposite directions? No. So acceleration is equal to force divided by mass. 12 newtons minus 6 newtons, because the force of friction isn't strong enough to overcome the 12 newtons. So 12 minus 6 divided by 4. So this box is now moving with an acceleration of 1.5 meters per second squared. Okay, try these out. They really aren't that bad. Number 6, what is the force required to move a 1,000 kilogram car, which is moving at 10 meters per second, around a curve with a radius of 20 meters? Okay. What is the force required to move? Okay, so I'm looking at force. Force is equal to mass times acceleration, right? Okay. Required to move a 1,000 kilogram car. So there's my mass. Force times mass times acceleration. So I need the acceleration, which is moving at 10 meters per second. Hey, wait a second. That's not acceleration. That's velocity. Acceleration is meters per second squared. Around a curve with a radius of 20 meters. Whoa, whoa, whoa. So now I think we're dealing, anything to do with curve has to do with centrifugal acceleration. So find it, which is also a formula for force. Okay, so now force is equal to mass times velocity squared divided the radius. Away you go, plug and play. Okay, so if I could give you any advice at all through all these horrible science-related courses that we all love to hate, get rid of the English. Get rid of this what is and, oh, that's a beautiful comma there, and oh, which is, that's just perfect. No, get rid of it, pull the information out, and mathematize it. So what is the force? So I'm looking for force. So then you go to your formula page. Okay, I got 4 formulas for force. I am going to use one of them. And then you look at the information, you pull the information out that I gave you separately. So you got your force formula ready to go here, and then you got the information, 10 kg, that's got to be mass, 10 meters per second, that's got to be velocity, and a radius, 20 meters. So I got velocity, mass, and radius. Dig through those force formulas, and I bet you'll find what you're looking for. Okay, same thing with the chem. All right. Here we go. Free falling and air resistance. When objects are falling, air resistance is always present. So this is what the air is pushing back on you. It's what's causing the meteorite there to burst into flames. Okay? And we got to take account in for this air resistance. When we take air resistance into account, the acceleration of a falling body is actually less than 9.8 meters per second squared because the air is pushing back. So you're not falling as fast as you think you are because the air is kind of holding you up a little bit. Air resistance depends on two things: your speed and your surface area. Sorry, I'm trying to hold up in front of the camera. All right. And if you think of like a parachute, what does a parachute do? Yeah, it slows you down. But what is it doing? Is it affecting your speed? Well, it kind of is in that. Now, you see my surface area, if I just jumped out of a plane, you know what I mean? I'm a bigger guy, but that's not a lot of air resistance. The air is going to hit me, go around me, and I would be mashed potatoes in about 30 seconds. But because I have a parachute now, my surface area is now, I don't know, how big are they? What, 20 feet across and 10 feet wide? And now the surface area is so enormous there that the wind can't get around, so everything is slowing down. Can I do this one here? Here's another one. Please watch this video on terminal velocity. It's really good. Really, really, really good. I have this video that I can play.
Let's take the easiest case. We have a couple of parachutes, Coney Island style, that are both open and start falling together. Okay, but let's have unequal weights. Let's have one parachute like that, the other parachute like that. This parachute over here is on a kind of a heavy dude here. And this parachute over here is on his little kid sister. Okay, and now they're both coming down. Very heavy, very light. I got a question for you. Which one hits the ground first? Check your neighbor. Through the air. Let me make it really easy. Through a vacuum. Which one hits the ground first? Vacuum. Same. Someone say, yeah, but this guy's a lot heavy. You say, yeah, we get a lot of mass. One effect takes care of the other, huh? And now, air resistance acts. You guys think the heavy one's going to hit first? How many people say, I think with the air drag, the heavy one guy going to barrel through the air a lot better than the little girl? Show of hands. All right. Nice. Okay. As they fall, the air drag builds up. I'm going to put an arrow for air drag, and I put the arrow acting up. Why I put it up? Why I put this arrow down? Because weight always acts which way? The U or the D? Down, okay. And the drag, a resistance force, will always be in a direction to oppose motion. Kind of makes sense, doesn't it? So you're coming down through the air, and the air kind of drags behind, and you're pulling. So it's a tug of war between this and this. And let's suppose these are both going the same speed. And I have this one about like that, okay? But let's suppose this over here, let's suppose this is like 400, and let's suppose the girl here is like 150, okay? Let's suppose the air drag here is 100. I got a question for you. Are both of these people at this instant undergoing acceleration? Check your neighbor. Do you know enough physics to say yes or no? Check. How many people say, you know what? They're both accelerating. I ain't going to say they're accelerating the same, but they're both accelerating. Show of hands. Most of the class, good. And how do you know? Because there's a net force. And if you got a net, what's the rule? If you got a net force, there's an acceleration. So look at that. They're both accelerating. Now, as they go.
And you see here, sorry, I've got a whole bunch of this guy's videos. This guy's really great. I have no idea who he is, but I've had his stuff there a long time. You can tell by the clothes it's quite a dated video. But that's the whole thing, right? Remember, if there is a net force, okay, then there is acceleration. All right? And if you're taking something out of its inertia, there's a net force. There's a force acting on it. And let's go. Will it go back?
Oh, if you got a net force, there's an acceleration. So look at that. They're both accelerating. Now, as they go faster and faster, what happened to the resistance? Vigorous, stay the same. The air drag depends on two things, gang. Depends on how big the thing is, how much air is plowing through, and how fast it's going. You're in the car. You're driving the car. Or your friend's driving the car. You're going 20 kilometers per hour. You stick your head out the window. Feel the air drag? Now the friend's going 50 kilometers per hour. You stick your head out the window. More or less. Now your friend's going 100 kilometers per hour. You stick your head out the window. What do you get? Dandruff job, right? I mean, that air resistance really builds up. The faster you go, the more the resistance, yeah? Okay, so these people are both going to go faster? How do you know they're both going to go faster? Because they're both accelerating. Okay? Now they go faster until the air drag builds up to. I'm making these both pick up the speed the same. I'm really oversimplifying, gang, just to give you the idea. Now they're going so fast that the air drag builds up to 150. I got a question for you. Do they both continue to accelerate? And the answer begins with an N. Okay? Now, which one ain't accelerating anymore? Why the little girl? What's the net force on the little girl? 0.
So you see here, the air drag is 150. Her force down is 150. So now she's reached what we call terminal velocity. That's as fast as she will go. And if you look at this person here, we've got 150 pushing back, 400 going down. So we have a force of 250 going down. So are we still accelerating?
What's the acceleration of the little girl? 0. That means the little girl goes, ding, hangs at rest, right? Does 0 acceleration mean not moving? No. 0 acceleration means not changing how you is moving. Okay? So she continued down steady. Let's suppose right now she's going maybe 30 kilometers per hour. 30 kilometers per hour at this point. Wait a couple of seconds later. How fast is she going? 30 kilometers per hour. How about the dude? He's going faster. He's going faster. He's picking up. She stopped picking up. What's the 50-cent word for stop? Terminate. Her acceleration has terminated. She says, I have reached my terminal velocity.
And you see here, this guy here, if he has enough space in between the Earth and here, this bigger person will reach their own terminal velocity. Okay? It all depends on how much space is between here and the Earth. Good little video. It's embedded in the on Blackboard, so you should be able to watch it again. More into terminal velocity here. It just kind of recaps what the video said. In free fall, the downward force is the weight of the object itself, and when it encounters air resistance, then the net downward force is, so the force total is your weight minus the air resistance, which is what we did up there, right? For the bigger person there was 400 minus 150, so we still had a net force of 250. When an object falls faster and faster, air resistance continues to build up and up. As it does, acceleration decreases. At some point, the weight of the falling object will equal the air resistance. When it does this, the net force acting on the falling body will equal 0. When the net force equals 0, acceleration stops. When acceleration equals 0, the falling object does not stop or hang in the air. It just doesn't gain any more speed. This is as fast as she's going to go. We're at the tail end here. Newton's third law. This one here, I'm sure you guys have heard there before. Oh man, the sun. I'm going outside after. For every action, there is an opposite and equal reaction. You see there when you fire the gun. Sorry, I'm trying to get in the camera. All right. And you see that the bullet went forward, but in order for that bullet to go forward, your shoulder had to go back. For every action, there's an equal and opposite reaction. It's going to be a little strange. Give me a sec here while I explain this to some in some capacity. We call the one force the action force and the other force the reaction force. Makes sense, right? Action, reaction. But it doesn't matter which is which. All that matters is that they are co-part in a single interaction. So you can't have an action without the reaction. Okay? But you need both to happen in order to have one, and neither can exist without the other. When walking, now maybe this might blow your mind a little bit here, but when you're walking, your foot is pushing against the floor. Agreed? Sure. But would you believe that the floor is pushing back against your foot? It does. And it's this action-reaction that holds us upright when we walk. Now, it doesn't really matter which is the action. We like to think of the initial reaction as the action force, and like me taking that step on the floor is the action force, and the floor pushing up on my foot as the reaction force, but it doesn't really matter. They're independent of each other. They can't happen without each other, and they're interchangeable, equal and opposite. But the action forces don't cause the, and as I said, one doesn't cause the other. They're independent of each other. They occur at the same time. One can't exist without the other. That's how it goes. When you jump on a trampoline, you are exerting a force downward on the trampoline. There's your action. The trampoline also exerts an equal and opposite force upwards, sending you high into the air. That's why, the bigger the jump, the bigger the bounce up, right? So, action and reaction forces don't cancel. For example, consider a student pushing a box. The box pushes on the student, but the student remains in place because the friction between her shoes and the floor. The forces on the box include the student's push to the right and the sliding friction to the left. The net force on the box is not zero, and the box accelerates to the right. Have a look at that movie. It explains that concept a little bit more. But just as long as you know that there is an equal and opposite reaction, the action and the reaction force there, we'll get into more of these. You will see that we will use force again. And right now we're dealing with kind of small objects, balls, these kinds of things, cars going around a racetrack or whatever. But soon we're going to get into forces of planets. All right? And it builds on the same thing. Is it any more difficult? No. When a skydiver jumps from a high-flying plane, they fall faster and faster, of course, until they reach terminal velocity, right? Does their acceleration increase, decrease, or remain the same? You guys, probably at this point in time, you guys could answer this. Let's read what it says here. As the skydiver goes faster, the air resistance increases, right? And it's just like what he was saying there. If you stick your face out the car window at 20 kilometers an hour as opposed to 100 kilometers an hour, you'll feel a lot more wind resistance going on. So as you go faster, the air resistance increases. The more the air resistance increases, the less the skydiver accelerates. When the weight of the skydiver equals the force of air resistance, here we go. Now we're back into that situation there with that guy in the video where now there are no net forces working on it. And if there's no net forces working on an object, there is no acceleration. We are now in an equilibrium kind of a state, an inertia kind of a state. What else we got? Oh, these are all right. What do we got here? Yeah, we're almost there. Two skydivers, a heavy one and a light one, both jump at the same time and have identical parachutes. Which jumper reaches their terminal velocity first? Now, you could And I totally recommend, if you're going to do questions like this, draw a little diagram like he did there in the video. See what's going on. That's what kind of a learner I am. I'm a visual learner. Some people are tactile. They like to have papers. Some people like to have auditory, social groups. However you learn, do it. But I would draw a little diagram off to the side. And the question says, which jumper reaches their terminal velocity first? Well, the lighter person does, because their weight is less than the heavier person. So therefore now the wind resistance, it'll take less time for it to equal their weight. Which jumper has the greater terminal velocity? Well, you've got a light person and a heavy person. They both jump out and they're both free falling. Okay, but the lighter one reaches their terminal velocity first because they're lighter and the air resistance is able to push them around more. So they reach their terminal velocity first. The heavier person is still has a force acting on them, so they're still accelerating. So the heavier person there will have a greater terminal velocity. And as I said earlier, everything you throw out of an airplane will have its own terminal velocity because everything has a different mass, a different weight. Okay. Which jumper reaches the ground first? Well, since it took the heavier person longer to reach terminal velocity, they're already that closer to the ground. Okay? And they're also falling faster. Okay? Because that little person is their terminal velocity was reached way up here. So they're falling. This person here is still accelerating. Eventually down here, there we go. Eventually down here, they will reach their terminal velocity, but it's already moving faster than the little person up there. Sorry, I don't know if this is working for you. If it's not, email me. If there's no air resistance, which jumper would reach the ground first? If there was no air resistance, which jumper would reach the ground first? And you remember there, I think it was it last week's slide there? Was it Galileo? I always use the analogy there. At the top of the Leaning Tower of Pisa, you've got a bowling ball and a banana peel. Which is going to hit the ground first if you release them at the same time? They will both hit the ground at the same time. All right? That's how that one goes. A car accelerates along a road. Identify the forces, action and reaction that make the car move. Well, the tires are grabbing the road. All right? It is the road that's pushing on the car. The car tires are pushing on the road. There's your action reaction. And in turn, the road is pushing back on the tires. There's your reaction. But remember, one doesn't cause the other, and they happen at the same time. Identify the action-reaction forces for an object in free fall in the absence of air resistance. The interaction between the falling object and the earth via the force of gravity. The action force is the earth pulling down, and the falling object and the reaction force is the falling object pulling up on the earth. Now, what is pulling up on the object? What is pushing down? Think about it. Gravity, air resistance. I like this one here. Which pulls harder, the Earth on the moon or the moon on the Earth? They both have the same, because they're in equilibrium around each other, right? They're not flying off into space. All right, there's no force really acting on them, so they are pulling on each other. Even though the Earth can pull a lot more, doesn't. There's an equal pull from each side. A high-speed bus and an unfortunate bug had a head-on collision. The force of the bus on the bug splatters the bug all over the windshield. Is the corresponding force of the bug on the bus greater than, less than, or the same? Now think about it. The bus hit the bug hit the bus. Go back to your original, your question 5 there, the Earth and the Moon. Which one had a bigger one? No, had the same. Situation's the same here. Okay? They're all equal. So the amount of force that the bus hit the bug is exactly the same force as the bug hitting the bus. Me walking on the floor is exactly the same force as the floor pushing back on me. The forces are the same, equal, opposite. All right? So the answer there for 6A, the bug and the bus make an action-reaction force pair. Magnitudes of all forces are now equal. B, is the resulting acceleration of the bus greater than, less than, or the same as that of the bug? Have a look here. Now, there's no numbers. So for the bus, you look at the acceleration is going to be very small because its mass is so huge. But the same amount of force done to the bug. Now, the bug's mass is incredibly small. But look at its acceleration. Because the mass is so small on the bug, look at its acceleration against the windshield. But the same force applied to the bus didn't even feel it. But it did, the bug did move the bus. Did it have a huge effect? No, because the bus has such a huge mass. Here's a little recap here. You guys can read this. It's a nice little recap of the 3 laws. You guys can have a look at these. These are some definitions. I like to use definitions. I'll tell you they're not this quiz, but these are really good. But guaranteed you'll probably see some definitions, some matching or something there on next week's test. So these are all really good. Have a look at these and have a look at the definitions there from weeks 1 and weeks 2. Know the definitions because I like to do a bit of matching there. The homework is assigned. The formulas are there. I think we're pretty good to go, other than you guys can go back and watch the movies there when you get a chance. But let me know what you guys got. I got nothing. That's it for me. Talk to me. Holy man, that sun is nasty. I love it.
I have a question about my lab.
Yes, what you got? Let me punch up my lab. Is that it there? Yeah, go ahead.
It's more, so I tried to get into it, and when I click the link on Blackboard, it brings me to like this PDF thing, and it lets me save it, but I can't actually edit on it at all.
Well, it's a PDF. You guys can print it off and write in there what you guys want. It's all good. No, the PDFs there, you can't manipulate them.
Okay, so we just gotta print it and then like
print it out and scan it and all that. Yeah, because I've got a couple requests there for Word documents, and okay, fine. You know what I mean? You guys can type it into the spaces they're provided, but I really don't mind. I'm not one of those teachers that likes everything neat and tidy. Like, science sometimes is a lot of chicken scratch. There's a lot of answers that have changed the world that have been found in the margins of a piece of paper. So don't be afraid to write on this, show a little calculation there, whether it's part of the question or not, or if it helped you get there. You know, I'm all about half marks, part marks. I've given 1/8 of a mark, you know, just because someone has showed some initiative, this and that. So don't be afraid to hand me in a messy looking lab. I don't mind it at all. As long as the answer's there somewhere and you showed me a little bit of what you were thinking, if that's what the question was looking for, then go for it. So yeah, print it off and away you go.
Okay, awesome. Thank you.
No worries. What else we got? All right, guys. I really appreciate your time, and thank you so much for giving me that hour reprieve. It actually made my week because I have a genetics lab there on Fridays. It's a good one. It's in conjunction there with Lakehead U, so I had to attend a meeting there and and take care of some business there. So I hope I didn't put you guys out too much. If there's any issues, let me know. You guys have your lab there this week. The quiz will open up there this afternoon. It's not too bad. Talk to each other, have some fun. And next week there is your test. I don't know how I'm going to work it, if it's going to be one day, but I will give you guys some flexibility on that somehow, some way. So talk to me and keep in touch. And thank you guys.
All right. Thanks, Ian. Have a good day.
Bye, guys. Be well. Bye, Jess.